to see you. So, dear ladies and gentlemen, it's my pleasure that we kick off the International Symposium on Quantum Software and Services. This symposium is a first of a kind of the IEEE World Congress of Services. And we start with an invited keynote. We will have a bunch of other presentations. We will have discussion panels, tutorials, and even a hackathon. And we will have in the main Congress a plenary panel on Thursday. But for now, we start with the invited keynote. It will be given by Jay Gambetta from IBM Research. Jay received the PhD in physics from Griffith University in Australia, and he was named a Fellow of the American Physical Society. But for me personally, it's very important that he is an IBM Fellow, and he got the fellowship for his scientific work around quantum computing, especially superconducting qubits, up to near-term application of quantum computing. He and his leadership, IBM was launching the IBM Quantum Experience, which is the very first cloud-based offering of quantum computing platform in the cloud. Under his leadership, IBM released Qiskit, and IBM has, as of today, if the number is correct, 38 quantum systems openly available over the cloud. And it's my pleasure to welcome Jay Gambetta to give a talk about current and future of quantum software and services. So Jay, please go ahead.
Thank you for the introduction. Let me just share my slide. Just give me 2 secs, I apologize.
Do you see Jay?
Yeah, I just can't find it in the actual the Zoom. All right.
Take your time. Here it goes. You see it now.
Is that sharing in the right view?
Yeah, perfect.
All right, thanks for the introduction. It's my pleasure to talk to you all, and I'm looking forward to answering any questions, and we'll see how this goes. So in my view, I look at quantum computing as exciting because when we look back in time, I think of this as the first time the history of computing has branched. What I think of a quantum computer is we're actually allowing to do different type of math on these machines. And in this math exploits really large systems, large multi-dimensional spaces. And so what we can do with these, I think of it as going to be very exciting. It's going to be a different set of tools that will be enabled. We know that it will help us accelerate problems in chemistry and material science because these problems themselves obey quantum mechanics. And we're also excited to see where it falls in other areas that use very large multi-dimensional math. And to me, I also have a strong view that quantum is not a replacement of classical. I actually think the future of computing is a heterogeneous type architecture, and it's about how quantum, classical, and other forms of computing work together to look for interesting types of problems. So what is fundamental about quantum computing, or how does it do this math? Well, it does it by implementing these things that we call quantum circuits. And these quantum circuits, I like to think of them as the fundamental unit of quantum computation. And in this picture here, I've shown a picture of a circuit. The circuit happens to be made of 4 qubits. And what it represents is, so you have both what we call space or width of the circuit, which is labeled, each one of these lines represents a different qubit, and then depth. This is how many different operations. So in this circuit, for example, we're doing a combination of 2 qubit gates, single qubit gates, resetting qubits, and measuring qubits. So if you want, you can think of time flows from left to right, and different types of gates are applied to the qubits, and they represent the different types of computation. And why do we care about these qubits? Well, these qubits, these circuits, they come in different varieties. We have some circuits that we've discovered that are very good for simulating quantum systems. Examples of this are in physics, high energy physics, for example, chemistry, material science. and I'll talk about some of these later on. We have examples of these circuits for more algebraic problems, most famous being factoring. This being Shor's algorithm, showing how to efficiently factor large numbers. But there are other examples using differential equations or machine learning and other types of algebraic problems that are emerging. And then the third category I like to think of as searching problems, or basically how you look at heuristics for optimization or different types of graphs. And so under these three categories, we're developing these libraries of circuits that will be useful for these different areas. So in this talk, the way that these circuits were previously run on these machines, when we first released the API to run on a quantum computer, we imagined that the user would be creating on their machine some type of program. That program would generate these quantum circuits. And then we would send these quantum circuits through the cloud, and then they would get executed on some hardware. And then they would just, if they would then send them back through the cloud. And if they needed new circuits would be run. And this was the architecture that we put in place to basically work for how a program would be developed on a quantum computer. This had limitations, and the first limitation is it didn't use the quantum computer efficiently. And so what this led to is what we put out in early beta in May, and we're on our progress to getting it rolled out to all our systems as we speak, is what we call the Qiskit runtime. And here it's a different architecture. Instead, like before, the quantum program is still developed on the user's computer, but instead of sending the circuits through the cloud, we imagine creating some type of container. And in this container, the quantum program will live. That quantum program will be able to generate the quantum circuits. Those circuits can get executed, they can run on hardware, and then they can be rerun depending on input and output from, output from the circuit and input from the program to run different types of circuits. This type of model allows us to run the quantum hardware at a much more efficient way and get the most out of our QPU. And so what this can do is dramatically accelerate many types of workloads. As an example, when we applied this to a chemistry workload, which I'll talk about more later on, in this workload, for now, you can think of it, it required running billions of circuits to do something useful. And if we were to run this on our previous architecture before we made improvements in multiple different parts, from algorithms to the runtime itself, to back-end software to allow it to execute much faster, to new control systems and better fidelities of the devices, this would have taken 120 times longer to run it last year compared to running it in May this year. And so what we see here is we see a combination, sorry, I just got a message. We see a combination of all these progresses coming together to allow us to run more efficiently. And also the actual waiting time of the distribution allows these algorithms to be much more predictable when they run, because we're executing them much closer to the QPU to get the most out of it. And so you see this runtime as a way, it's an evolution of an architecture that is putting some classical computing closer to the machine. I like to call this classical with a little c, and I'll explain more of what I mean by that later on. But the most important thing to get across right now is to get the most out of these machines is bringing some classical compute to allow them to run at a faster rate. So here's an example of how we envision a user using this. So in this example, they would be coming up with some molecule, it's lithium and hydrogen. They would construct the problem. They would then basically convert this problem into a problem that the quantum computer would understand. The quantum computer talks in terms of, as I said before, qubits, and we need to construct an effective representation of the problem that is different to the chemist representation. Then we would choose some type of ansatz, and then it would be executed with the ground, this command down the bottom, the ground state solver, which would take the qubit converted problem, run it on the Bqe algorithm, and then solve this problem. Putting this together, we imagine the future for for the cloud working to do this type of chemistry simulation as this video sort of outlines. As I said, the molecule would be written in some type of geometry. The problem would be specified, and then you would choose some backend, in this case, some quantum QPU to run it on. You would construct the actual program that would be run. So this is going to be running Bqe, and then you would solve it. Then this program will be sent from the user's computer to some over a combination of a hybrid cloud, hybrid server, as well as a quantum processor. So here we see the program running. First step of it in the cloud is to get it authenticated to make sure it is able to run. It then creates this containerized program. This containerized program uses what we call a runtime manager to get the different types of circuits to be run. And as I said, it could be billions of circuits that would be running. Each one of these circuits is sent to the hardware, run on the hardware. We get all these results, lots of ones and zeros back. This can be then computed and determined whether we need to run more circuits. And in this case, the answer was yes. It would run and get a different set of results back. And then the final answer can be sent back to the user's computer and then able to be turned into a result showing, in this case, the solution to the chemistry problem. So we imagine this is how we see the future of quantum computing working. And I'll explain some of the ways on the paths for us to get there. And of course, you could go even further. And we like to say that we imagine quantum computing when it's successful to be frictionless. And what we mean by that is not that it's easy to use, but we can easily integrate quantum computing into any type of software. So if a user really wanted to develop in Excel, not suggesting Excel is the best way to develop chemistry problems, you could imagine taking these APIs to these secure portable Qiskit runtimes and being able to support them as a program that can execute in the backend. And in this case, it would be taking the same problem, lithium hydrogen, executing it and finding a simple answer. So what do we need to do to get all of this working? We need to make it easy for developers to use. It needs to have a low barrier of entry. We need to have it simple to specify that they're using quantum computing. We want to use a developer to be able to say, run this on a quantum computer, use this type of capacity, run this on a classical computer. We actually believe that it should be serverless. We just want the developer to be able to execute the code, not worry about the infrastructure or setup, just get it running. And we want it to support combinations of embarrassing parallel algorithms and things like this so we can get the most out of the machines. Before I go into details, to give a feel for how I see the architecture for a quantum computer as well as the application stack and any technical services that would exist on top, I think of a quantum computer, and I think by now you sense my opinion. It's not just the QPU hardware down the bottom. That is important and is fundamental for us having quantum advantage or doing something that we cannot do classically, but also is a combination of the electronics to get the most out of it, as well as the software to facilitate running it. So how do you set up the environment? So I called all combinations of this software and classical system, the control systems, and the quantum hardware as the quantum computer. And I think of the quantum computer as the ability to execute quantum circuits and to execute them at a fast rate. Then I imagine as we build out this stack, we will need to be able to take the quantum computer to where the data is and to be able to run applications and build real-world programs. So there will emerge an applications layer that will focus on how you actually get a problem, split it into the different types of components that it needs to run on, some being quantum computers, some being on classical computers, and some like GPUs, and then bring it all back by analyzing it. And I imagine this being the application layer. And then ultimately sitting on top of this, there'll be a technical services layer. And in this, this will be on how we actually train, develop quantum computing, work out how it gets integrated into many workflows. And what we're seeing actually, like IBM, we're seeing end-to-end providers emerging, but we're also seeing this great ecosystem of different types of startups that are focusing on different types of the actual stack, some being just hardware providers, some being software, and others being specialized in specially building some type of, say, controls infrastructure that is useful for the system and things like this. So from when did we start to see quantum computing, in my opinion, change from the academic lab to something that is more actually used by many hundreds of thousands of people, and in some way start to emerge into what I like to think of it as an industry? I actually say it dates back to when we put this on the cloud. In 2016, we put the first system on the cloud, and this was a goal to be able to show how many users could be able to run on this system. Since then, some numbers that I'm very proud of is how many papers we've had run on our system. Today, we've had over 500 papers. So this is actually showing scientists, researchers using this as a tool to do actual science on the system. And then on top of this, we've had over, at the start of the year, there was over 2 billion circuits run on our systems per day. This is definitely on track to doubling that by the end of the year. And we've basically seen an exponential growth of the amount of use of these machines. So you can see this emergence of adoption of this being useful. Then taking this to the next level, we tried to think of how you actually turn these into systems, not just, and by that I mean, how do you get them more stable, reliable? How do you get the reliability up? How do you have them more so that a user, if they're going to use it, they're more sure it's available to use, the calibrations are run more frequently, and run less frequency, but have more reliable numbers. And so all of this went into what we think of as building a system. And in January 2019, we released our first IBM Quantum System 1, and this is more a full system view of these machines. Since then, we've put multiple of these System 1s in our IBM Research labs in Yorktown and Poughkeepsie, but we've also installed one of these in actually Germany in the Fraunhofer Institute, and one in Japan in the Shin Kawasaki lab in partnership with the University of Tokyo. And so we're seeing this emergence of different types of places getting, I like to call, like, we're starting to build almost a data center in multiple different locations. So some of the systems that we have online to date, I think this is a little bit wrong. I think we have 22 systems online. So that changes quite often, but we have a combination of systems that are either what we call our core systems as well as exploratory, and these range in different sizes and different quality. So for instance, the Falcon is an example of our 27 qubit machines, and you see here we have multiple different realizations. We have a Falcon R4 and a Falcon R5, and then the difference in this is bringing in new features. For instance, in the Falcon R5, we focus on how we can bring to the 27 qubit machine an ability to do that measurement operation faster and reset the future qubits, which is important for basically getting what we call dynamic circuits to work on in the long term. And so you see this is this idea that what we're trying to bring is different types of I like to think of it as the agile philosophy to hardware. How do we bring new features as fast as we can to these systems and iterate on them, whilst maintaining our more reliable, which in this case are our Falcon R4s. And then you can see also different types of examples where we push the size of the system. So Hummingbird is going to a 65 qubit, so basically doubling the size of the qubit system. And then there are various other machines that are there of different sizes, with some of them being smaller in size. So as I said before, what's really good for us is seeing the adoption of these systems. And we've seen this exponential growth with just recently crossing 1 trillion different quantum circuits run on the quantum system. And so if you think about that, 1 trillion is a lot of circuits that have actually been run on these machines. And so I see the future being an industry where a trillion circuits, let's say, are run a day. And I'm hoping that these trillion circuits can do something useful for the different applications that we are developing. So I'm going to take a little bit of a detour. Sorry, a little bit of a detour and give some intuition of what sort of matters for understanding how these systems are becoming useful. And what I'm going to hope in going through this is I show that both a combination of hardware and software is important for this. And then later on, I'll talk about how I see this this hardware being consumed more in the cloud. And so to get into that, I think there's 4 key metrics for understanding a system that can run quantum circuits. The first is quantum volume. What I mean by this is just a metric that can determine how good are these quantum circuits in running quantum mechanics, like how close are they at actually implementing what the math of quantum mechanics says, and are we showing that over time we can continually improve the quality of these machines. For this, we've chosen quantum volume as a metric. I don't really want to go into the details of it, but you can think of it as a heuristic for measuring how good a quantum circuit has implemented the gates that you chose to do. And we've seen today we get 128 quantum volume, and we're well on our way to doubling it. And if we compare that to where we were before, which was 32, we have this goal of doubling, at least doubling the quantum volume each year, showing that we can continually make better, higher quality circuits. Okay, so that is one metric that just focuses on how good is it obeying quantum mechanics. Then a second metric I like to call scalability. This one is as you make more of these devices, you need to be sure that you can keep making them bigger, you can keep them being reliable, and you can keep them keep lowering the cost of how you build them. And so all of these are important that go into, is this architecture scalable to larger and larger systems? And as an example, things that can go into the quality is the yield of the device high? Can I, if I fabricate it, am I sure that once I cool this down, it's going to work? Things that can go into the cost. The cost of the electronics when I first got into this field was very expensive, at least 100,000 per qubit. Getting that down to a couple of thousand or 1,000 per qubit really shows that it gets cheaper to run larger systems, or keep the price of running larger systems not get out of control. And so all of these are important for making sure that as we progress down this field towards building a useful quantum service for running quantum circuits, that it will be actually possible to achieve something with these machines. Now, the third dimension I like to call QPU speed. I think us in the field have kind of ignored this, and there are reasons for it in some way, because if you have a quantum algorithm that gives you an exponential speed up, you don't really care about the actual time it takes to run when you're comparing it to classical. But as we get more practical, running something, say, in a day versus running something in a year really matters. And so what I mean by QPU speed is how fast can we run these circuits? Can we make sure we get a throughput of these circuits so useful work can be done in the days, possibly months, not years, decades example. And so there's a lot of things that go into how, like the Qiskit runtime is an example of how you make it faster, but ultimately there is also hardware that can go into it, and there's fundamentals of the physics of the device, making sure it can run in useful time. So making sure the architecture supports running circuits at a fast rate is definitely important. Now for us, because we also want to provide services to users and we want to see that it's actually getting used, we have a more, I'd like to call it a soft metric of adoption. How easy is it to use? Are we seeing growth in it? Are we seeing that people are doing useful work with it? That gives us the sense that we're making progress towards a useful quantum computer. So if I dig into these for a little, so if I dig into quality, so there are things that go into the fundamentals of improving. Basically, is it obeying quantum mechanics? One is its coherence. Coherence is, for us, is how long does a quantum computer stay quantum without decaying into classical? And so what's important is we continue to keep improving the coherence times. Since I've been in this field, I think the first transmons we were making were around the 100 nanoseconds. Here's a picture of a T1 crossing a millisecond. So it shows that we're basically increasing them by a factor of, what's that, 10 to the 6 almost. Oh, no, 10 to the 4 almost. Then there's also gate fidelity. How good are the gates? Are we making progress in making the operations on the gates get closer, get lower and lower numbers? So different types of gates, pushing them towards what we call the coherence limit. That just simply means be limited by the decoherence of the quantum computer, but actually pushing the gates to higher and higher fidelity so that we can do them with more and more precise. Then a third is compiler. As we try and do an arbitrary circuit, which we want it to work on a more like a general random circuit, how good we can compile a quantum circuit down into these gates can affect how well the average quantum circuit can run, as well as different types of tricks like implementing, if we know certain gates work better, using those ones more often. If we know certain gates can affect nearby gates, being aware of the gates that are being done to build the compiler to use non-nearest neighbor gates or something like that. And third, inserting different types of techniques to get rid of low noise errors and allow us to be only limited. We call this dynamical decoupling, limited by high noise, high frequency noise errors that can, such as T1. So all of these go into us continually improving the quality of the systems, how well it obeys the quantum mechanics. And as you see in this plot down the bottom right, we continue to have seen that we can continually improve the quantum volume, and with our most recent being 128 on the Montreal device. And in that one in particular, it was limited, the different type of gate as well as the compiler made the biggest difference. So yield. So our goal is to keep increasing the size of the system. As I said, our standard systems are the 27. We have some of the 65s available, and we're working towards what we call the 127 to be released by the end of this year, and next year, the 433. But as you go and make larger devices, there are different physics that you have to come in to solve. The first is getting yield, getting high yield out of the device. So in this little graph that I've shown here in red is the different, the variation in the qubit frequencies that you just get from fabrication. So if I just made a device and I was to just following natural fabrication, try and make all the qubits have the same frequency, we get basically a distribution here of that's shown in the red, which I forget off the top of my head, but it's tens to hundreds of megahertz in variation of frequency. And so now if I was to ask, can I make two qubits and have them not cross, like I don't want to have a collision. If I'm making a large enough device and I want all the qubits to be slightly different in frequency with this, but not further than a couple of hundred megahertz apart, then this leads us to the probability of them having a collision to be very likely. And so what the team had to do is develop a post-fab method of laser tuning the qubits, and that's what's shown in the black. And by this, we can tune the qubits. We make a device, we go in and tune the qubits using a laser, measure some resistance, and we can make a device, and the likelihood of it succeeding is much more higher because the spread in frequencies that are available is given as by the black in this example. So this is just one way that shows how you get higher yield. Now, to go to larger devices, you'll have the problem of having too many input lines. And so for the 65, one of the challenges we needed to solve for that was how do we get more multiplexing out of the system? How do we get less output lines so that we can actually cool these systems down? So build multiplex into the reader. This is what needed to be integrated into the QPU to allow the 65 to be possible. And then to get to the Eagle, if you imagine you had a chip and you had the problem of trying to address all the qubits, you're going to see an I/O problem. And by that, I just simply mean, imagine drawing a graph and trying to draw a line to each one of the qubits and not have them cross. And it turns out to be really hard when these get larger devices. So to solve this, we have to do what we do in classical. We have to build multi-level wiring stacking, which is shown in this figure, into the I/O lines to allow us to have the lines to cross to drive each one of the qubits. And this allows us to scale the CPUs up to very large sizes. Then to solve the 433, it actually turns into a problem of scalable I/O. And what I mean by this is the I/O in the fridge. You've probably seen all these nice photos of all these coax lines that look like it's really complicated. Here's an example over here. Can we increase the density with some flex, much like the old printer cables that we had? And that can give us a much higher throughput of lines from room temperature to the cold parts of the fridge. And by building different type of componentry there, we can solve the scalable I/O problem. Okay, so all of those ones go towards speeding up the scalability. Now speeding up the QPUs. Obviously, first is better control electronics, so I can take a user's input of which gates to do and turn it into waveforms that can run really fast. We've gone into FPGAs to do this, and we could imagine a future with using cold CMOS or even ASICs or something like that. But continue improvement on the controls to be able to take it from user's desired input and turn it into a waveform that played on the system. To get information out of the system, it's so better readout. If I try and read out a quantum system better, it usually means I open it up to decoherence, and so then I affect and I can lose the quality of my system. So trying to solve a problem to allow me to get information out of a quantum computer without without creating unwanted decoherence turns out to be one of the most difficult things to do. And the way we go around solving it is we design readouts that allow information to come out at the cavity frequency, but not the qubit frequency. And so this is an integrated componentry that allows you to get information out about, say, the state of the qubit, but not affect the coherence that I talked about before. And so this is what we mean by better readout. And then the Qiskit runtime is an example of how you bring the software services closer to the quantum processor so you can run the circuits at a higher execution. And as I talked about at the start of my talk, down the bottom here, I show some of the results for this lithium hydrogen that shows running many of these circuits much faster. That allows us to get a higher throughput on the system. So when I take all these three and I put them together, quality, QPU speed, scalability, and adoption, this is actually precisely why we choose superconducting qubits, because in my view, like many of the systems that are out there, we're seeing them improve how well they obey quantum mechanics, and it's amazing in the progress we're seeing with trapped ions, for example. But on other dimensions, when you look across it, they don't perform as well as superconducting qubits. So if we're trying to optimize a system to be able to run quantum mechanics at a high quality, at a high throughput, and scale to larger systems, this is why us at IBM are going down the superconducting qubit path. So we put this roadmap out a couple of years ago. Down the bottom, you can is showing the hardware, which I mentioned before, showing in addition to the 433, the 1,000 qubit machine. And it's our goal every year to demonstrate a larger machine. And now, as I talked at the start, the main focus of the software was to focus on circuits. And then we just started to talk about Qiskit runtime and the ability that allows the QPU to run at faster speed. But as you see, what we're now emerging and making this transition in the near future is to more things that are going to use, say, pre-built runtimes, circuit libraries, and HPC. And it's my hope that we're stepping up the quantum software and abstracting away more of the quantum physics to build up what we call programs to allow a user to develop at a higher level and to run that. And I'll try and say a bit more about, before I go into that, I'll say a bit more about why. So why do we care about quantum mechanics? Well, about quantum computing, sorry. Well, at its highest level, what it can do is it can look at different types of programs that can solve quantum, say, that are problems that are driven by, say, quantum mechanics. So understanding, say, better catalysts and understanding storage, all these turn out to be huge, difficult problems of solving quantum physics itself. So if I can mimic it by a quantum computer, I have the potential to look for better catalysts and things like this. As well as machine learning, as I talked about at the start, we're interested in understanding, can we have access to different types of math to look at different types of ways that machine learning can be done and see if it can boost the performance of that. And then there's different examples, more chemistry examples, high energy physics, and examples for finance, which I'm sure Stefan will go into in much more detail in the panel. So I wanted to give you a feel for a bit more of how these algorithms work. So here's this Bqe algorithm. And so what you see in this Bqe algorithm, I don't want to get lost in the details, but the user specifies a problem in terms of Pauli terms. And what this just represents is a qubit representation of the problem to be solved on a quantum computer. Then they come up with a ansatz. This is an example of a circuit that goes into it, and a rule of how to convert that circuit output into an energy estimation. And then we run it on a quantum computer, estimate the energy, feed it into a classical computer, determine the controls, and we do this loop multiple times. And in 2017, we studied H2, lithium hydrogen, and beryllium hydrogen to look at different size problems that we could run it using these type of circuits. But here what you see is I've chosen a circuit family and I've worked it with a classical computer. And so what I want you to get through now is I'm doing something that's a little bit more advanced. I'm calculating some new output, different set of controls that will go and run the next set of circuits on the quantum computer. And then we can go even further. So we can imagine that we have a way of trading resources. So we can run multiple different quantum circuits, and then by combining those different quantum circuits together, we can look at an improved quality. These are techniques similar in classical where like Richardson extrapolation, where you can increase the precision of a differential equation solver by looking at different orders and adding them together. There's also different techniques where you can do the same for the measurement. So this is more focused on the gate side, where you can take calibration effects and the measurement to add different circuits together to improve the outcome of the measurement by correcting for some of the measurement errors. So putting these techniques together, you can see, for example, many times improvement in the quality of the run. And I don't want to get into the math of why this improved it, except to say what you're doing here is just trading some quantum circuits, so running more of them with some classical post-processing to calculate a higher answer. We can take that even further, and what we've seen recently is we can even extend these techniques all the way up to 26 qubits. And here we can start to look at problems and compare how you would actually compare an approximate quantum solution. So running the quantum solution with error mitigation, but not of course, it's not run, you can't get rid of all the errors, to an efficient classical example. And we can start to see there be a crossing where the quantum predicts the outcome better than the classical, by putting all these techniques together. And these techniques, most of them are classical, analyzing the results, correcting the measurement mitigation, correcting the the error mitigation for running the gates, as well as the measurement mitigation on the readouts to make the results appear better. And here's another example. In this example, we imagine we have a larger system and we have this large problem, and it happens to be a chemistry problem again. And due to the symmetry of the problem, I can split it up into two smaller problems. And now what it works out is I can say, well, I can follow this technique of splitting the circuit in half, and then I can look at expectation values over different types of halves, take combinations of these different expectation values, combine them together through simple multiplication to determine the actual answer for a larger problem. So I take a problem and I'm splitting it into smaller. I like to think of this as the quantum version of map reduce. I'm essentially taking a large problem, reducing it into smaller ones, running them, and then combining them together. And I can, in this type of problem, we took the example of water. The team took the example of water and demonstrated that a 10 qubit solution of water can be run on 5 qubits by combining these different problems together. Okay, other examples of problems that we've been, which I don't have time to go into them in much detail, but happily take questions if there are them, looking at different, some of the finance ones, as well as exploring basically logistics and types of those problems, as well as some battery physics with the different chemical companies as shown on the slide. So what I wanted to say here is, you see where the future of this is going is now you can take your quantum circuits, and whilst we've developed a Qiskit runtime that allows me to run them much faster, so I'm using classical computing to run them at scale, a lot of the workloads that we are coming up with and that our clients are working on us with are now combining classical techniques that require more classical resources. And so you see this architecture starting to split. So I like to think there's classical compute with a little c, and the little c's focus is how do you actually make the quantum hardware execute at a fast rate. And now there's classical C with a capital C of how you bring in more scalable classical computation to do these applications that either allow us to look at bigger problems, correct for, mitigate for errors, and and other techniques as I've discussed. And so what we imagine is that we imagine the future of something where we see bringing a orchestration layer. In this case, I'm taking the IBM code engine as an example, where it can talk to both of these. It can talk in a serverless layer to the quantum, the Qiskit runtime that executes the quantum part, as well as some classical compute. And here it could be bringing in general purpose compute GPUs, and it could also be reconstructing and developing those circuits. So how do we actually work towards this architecture, a service layer that can talk to both of them? That's where we'll see going over the next few years. And of course, in a lot of these problems, we're going to want data that can exist both between the quantum layer, where we're executing focused on speed, as well as how we analyze the data. And so you can see that that entanglement forging example was one idea, but there are various different, even more complicated ones where you can really start to trade classical for quantum and go to really large systems. And so you can imagine more complicated ways of coming in and cutting we call it circuit cutting or circuit fragmentation, of ways of breaking the problem into smaller problems to be able to allow it to execute on a machine. And here's just some trivial examples where you could imagine you have some large circuit, you can break it into small circuits and add those small circuits together, or you can even cut across depth. And now you can imagine not requiring as much constraints on adding on the coherence, because you can run shorter circuits. And I don't want to, every time you cut, I don't want you to think this is a solution, that this is allows you to always solve this, just get rid of a quantum computer altogether. Every time you do one of these cuts or you do something of this type of a trick, it brings exponential classical resources to your quantum. And that's why you really need to bring this this classical with a GPU or some HPC resource to the problem. And it's not, and it's allowing us to do more in a faster rate than would be possible as we continue to extend and increase the quality of the quantum circuits that run. And just to finish, there's a simple demonstration that we're prototyping that Mikhail will talk about later, and my video didn't run, so I'll just skip it. But essentially, how you could imagine a Python version of this being able to bring together both the, both the classical and quantum part of the logic. And in this example, you imagine basically you have a part of the circuit that is doing the quantum, a part of the circuit is doing the classical, and then you have a simple main part of the routine that can basically talk between both of these in a way that can execute them and allow you to execute this future vision that I see happening, where we have classical and quantum working seamlessly together. And so if you've got more information and you want more information, our quantumcomputing.ibm.com has lots of resources, as well as our quantum computing services and system. And we're showing all our systems. And we're also committed to open source, and qiskit.org is where all of our software is that we're developing at this point in time. Thanks.
Thank you, Jay. So there are only a few people that joined in the meantime. Are there any questions from the people who joined? Ismail, you are the host. Maybe you can switch on the mics of everybody. So if there are no questions, then I may start. So you brought something from my perspective very important, and namely the use of persistent data. In our use case, we have tons of persistent data. And what is your thinking? How do you tie it in? Because it was only very briefly on one of your last slides that you tie in persistent data. Any ideas that you can share with us, Jay?
I wouldn't say any ideas to share other than we have to do it. Okay. So I know that's not the answer you wanted to hear, but as I learn more about how the classical development is going in the sort of serverless way, the ideas and the solutions that we're doing there, how do we make quantum mimic that? Because I'm going to have classical memory in the quantum, like you said, some use case. I don't want to have to be transmitting that all around. If I've calculated new controls for my system using some really heavy classical compute, I want to have that accessible by my quantum, so I'm not wasting it. So we're trying to make sure we work out. In our first demonstration, we're not going to actually use it. We're first going to just talk to the classical with the big C as well as the quantum. But I think it's important. The reason why I just had it there and didn't spend much time on it is I think it's important to note that we have to do it, but how we do it, I think we've got some work to decide.
I'm asking you, some famous algorithm assume the existence of some QRAM. Are you working on something similar like that?
No, so I'm thinking more persistent classical RAM, yes. Not quantum RAM. I don't think we will ever build a way of taking a quantum, well, ever's a long time. It seems unlikely we'll build information where we can put it into a quantum RAM that you can just pull into your quantum circuits. So I like to think of my quantum circuits as a set of instructions I run, and I try to put any of the memory into classical and then just use the quantum circuits to do simple functional calls on them. I think it'll be a long time before we get to anything like QRAM. And I'm not even sure for those algorithms that use QRAM, when you take into account the costs of getting the memory into them, that they are worthwhile. So there's some open algorithmic questions as well as some hardware questions of how it would be done.
That's true. So in the meantime, anybody else with a question? Otherwise, I continue. So one of your first slides basically has shown that although IBM is a full stack vendor, you imagine that at the different layers vendors are coming in and that different hardwares has to be supported. This always rings a bell in my head. Do we need a standard to access QPUs like HTTP, for example, allowed us to abstract all the different web server implementations under the HTTP interface? Do you envision some sort of APIs that you standardize with other vendors so that software basically can rely or can be built on top of this API?
I think we will work towards standards. I worry if you go too fast that it can be bad for progress. So if we take a look at what we've done, we have tried to standardize OpenQASM, which is an immediate representation, but that's a very low level. I don't think most developers should be doing that. But I feel confident that the OpenQASM 3 now, of course, we'll probably get to 4 or 5 when you find errors and whatnot, but I feel that that one's getting close enough that it represents a nice representation of a circuit to be run on hardware.
But the question was more in influencing the execution, right, of the circuits.
Yes. Okay. And I think if we can build the things like Qiskit runtime, we first start with the open source, I think a similar standardization can happen there, but I wouldn't jump to it. We've got to see how it works out. But essentially what I think we've got to do is give the ability for a quantum program, which is a set of code that will generate some circuits and then run them on some hardware and turn those results from ones and zeros, say, into a double or something like that. That I think we've got to first show that we can run that in a really serverless way, like send it out, run the results, get them back. And then I would like to think of how we can standardize without defining standards yet. People can upload their own versions of different types of ways of generating the circuit and analyzing the data that needs to be close to the machine. And then once you get that classical C with that classical compute with a little c sort of worked out. So I think of OpenQASM first as classical compute that needs to be done within the lifetime of the quantum computer. So we've kind of standardized that. Then there's classical compute that really focuses on running the quantum computers at a really fast rate. I think we've got a bit of learning that we're going to learn, but the first thing is we've got to get it into people's hands to see how the runtime goes. If we can do that, then you can imagine that becomes a very standard way of just doing that. And then if you want to bring more classical, which we know we will need for the applications we look at, then I think we should leverage the standards that classical compute has already done, right? Like of how you host it. So my goal is, how do we bring quantum to serverless HPC? I think we want to demonstrate that in the cloud so that people can call, like you just call quantum, just call classical. And then how we like, I don't exactly know where the line between classical with a big C is and classical where a little c is.
That's how you huge reason.
Yes, how you define that line, I think we've got to try things first. And I worry about defining that line before we've tried too many things.
Yeah, sure. We need to have use cases, right? Do some experiments.
Yes.
So back to the other attendees. In the meantime, any questions you would like to ask to Jay? If not, I have a final question, a very low-level detailed question. We are also experimenting with splitting circuits horizontally and distribute over different QPUs and then aggregate the results. But of course, this depends on the input being not too much entangled. did you do some work what entanglement basically restricts your idea that you also have to split the circuits and run it in parallel on different QPUs, or did I misunderstand it?
Yeah, I think you're spot on. I think so. The entanglement formation is a nice way of using the symmetry to do the splitting.
Yes.
And so you don't get the cost of it. If you were just to generally split every time you cut a wire, either in time or space, you would get you would hit some of the exponentials. Like the generic way is to insert a qubit, do single qubit quantum process tomography, and then join them all together. I think there's a continuum between the entanglement forging and the more general way. And I think that continuum should be driven by how much entanglement you need to break between the different parts of the solution. We don't have an answer for that yet. I think that's still open research, but that's precisely what we're even internally thinking about in the research question is, yes, I can do it exponentially, but obviously I don't want to do exponentials if I don't have to. If I can look at a problem and use some symmetry or use some knowledge of how much entanglement is, like entanglement for multi-site systems is complicated, but maybe you could reduce it into smaller problems and say how much entanglement is shared across each link, then that could give you some intuition on how to cut it. So I would say there's a easily established top end where you cut it, you do quantum process tomography for every cut. So you imagine adding essentially basically an exponential continuously. There's the nice entanglement forging, which that if it's got this type of symmetry, add it together this way. But I think there's a whole space between them. And maybe I didn't get that across, but I don't think we have an answer yet on how best to fragment circuits up.
Okay.
So I think all my answers are said, good questions, but these are exciting research directions.
I have my research hat on, and this motivates me with my team to continue working on that issues.
But I think the high level principle of if you can make quantum advantage come faster using classical compute, we have to build an architecture to allow that.
Absolutely. Yes, that's what you're.
And that's the guiding principle that we're trying to follow.
Yes. So if there are no more questions from the audience, then I would like to say again, thank you very, very much, Jay, for taking the time to deliver this keynote. Thanks, and all the others. I hope that you enjoyed watching the video. So Ismail, if you can stop recording, and then we're basically done.